Time seem to help?
Yes.
I hope so. I'm scoring the questions at the same point value, so that at a glance we'll be able to see how the extra time related to improvement relative to exam 1. As I believe I've said, if this quote-unquote experiment of extra time has related to score improvement, then I'm going to see to it you get extra time for all the exams. You're not getting paid to do this now. I don't want you under time pressure. University cooked up this policy of 2-hour limit for exams. They can stuff it if it interferes with the educational process. And of course, if powers that be hear me to have just said what I just said, they'll probably squawk, and I don't give a damn. The purpose of this place is to support education and to deal with students' needs. So, we'll make it work. We'll see what the results have to say. All right. Now, a more deep, broad view of thermodynamics relative to Chapter 20. Again, Chapter 20 parallels what most of you have already seen in Chemistry 2045 in the chapter on thermochemistry. But I repeat, the major shortcoming of that chapter is that it invites you to look at reactions taking place and the change in enthalpy regarding such. The shortcoming is that from a change in enthalpy standpoint alone, you cannot determine if a reaction is spontaneous. Like water solid becoming water liquid. If we take ice cubes and put it here on the bench top, exposed to the conditions which are with us in this room. That is an endo process, and it's spontaneous. Why is it spontaneous? If the change in enthalpy for the process is again it, because solid converting to liquid is, of course, bond weakening, bond disimprovement. Well, you know now the answer. It's the favorable change in entropy, which when multiplied by the temperature is favorable and has a magnitude which exceeds the unfavorable change in enthalpy. Upshot, delta G for that process has a minus sign. Process is spont. So with that in mind, we go to Chapter 21. And now take a deeper look at G and delta G. And of course its relationship to H and delta H and S and delta S, which can never be separated. Since, as we've already seen, this most important fundamental thermodynamic relationship demands that you recognize the dependence of delta G on these, which I refer to as the fundamental puzzle parts of thermodynamics. Now, regarding phase diagram for water, which you've already seen, but can't possibly have really understood when you saw this in Chemistry 2045, because a phase diagram is a G-state diagram, a free energy diagram. And the textbook, as it is presented, doesn't talk about free energy until well after this chapter where you've been introduced to phase diagrams. Screwy, in my opinion. Now, how is this G-state diagram constructed? This part you know. As a function of pressure versus temperature. If, when you examine the diagram, you pick any pressure and any temperature. And see where the pressure-temperature correlation point is found on the diagram? You'll know which phase or state of water is stable from a thermodynamic standpoint. So let's talk about some specific parts of the diagram. Like the three lines which separate the three phases. A, corresponding to the most common triple point for water, where water solid, water liquid, and water vapor are in simultaneous equilibrium. With point A connected to point D, that construction separates water solid phase from water liquid phase. And point A connected to point B. I'm doing this by memory, so I'm hoping I'm announcing these connections correctly. The line AB should separate the solid phase from the vapor phase. And then last line is AC, which separates vapor phase from liquid phase. The liquid phase on top. Not surprising, because on the vertical axis you see pressure plotted. And you know that as you increase the pressure on a sample of material in the vapor phase, you tend to induce condensation. Do you not? Bringing the sample particles closer together, providing the opportunity for interparticle attraction forces to ultimately dominate the behavior of the sample, which will cause condensation. Line AD, the solid-liquid boundary line. On any point on line AD, the thermodynamic stability of water solid compares how to the thermodynamic stability of water liquid? At any point on line AD, how do the thermodynamic stabilities of these two phases compare?
Equal.
They're equal. That's why equilibrium exists. That's the only way equilibrium can exist, is when the overall thermodynamic stability of reactants equals overall thermodynamic stability of products. But at any point on line AD, how does the enthalpy of water solid compare to the enthalpy of water liquid? Are these enthalpies equal? Which one has lower enthalpy? Solid or liquid? This you should have learned in 2045. The more stable a sample of material as a function of bond strengths, the lower is its enthalpy. So, a way to recognize this conceptually, I think, is to view enthalpy with the symbol H as heat content. Because you know, the greater the heat content of a sample, the greater its tendency to exist in what phase? Gas. More heat, solid becomes liquid. More heat, liquid becomes vapor. So with that, the lower the heat content, the lower the enthalpy, hey, solid phase predominates. On the other hand, given that what we've just recognized about the water-solid, water-liquid system is if enthalpy was the only thermodynamic property which existed in nature, would you have liquids? Would you have vapors? Would you have motion? No. Enthalpy says, I like bonds and that's all I like. I want no motion, I want strongest possible bonds. The universe, if it existed, would be a motionless lump with bonds of infinite strength. Ha ha! But comes along the other thermodynamic property which exists in nature called entropy. And entropy says to bonds, I don't like you. I like motion. I can't stand attraction. I want all particles to exist as if they are completely and totally independent of each other. I want vapors, I want no bonds, I want no liquids, I want no solids. So when we view nature, we can view it as a battle ongoing between enthalpy and entropy. And whatever the position is of the battle determines what you are seeing from a phase existence standpoint, if you want to put it as simple as possible terms. Solid, liquid, gas, bond strengths, all that stuff. So, enthalpy says this only, entropy says this only, and what do we find? As a consequence of this relationship, which cannot be evaluated, because we cannot measure absolute enthalpies, even though we can measure absolute entropies because of the third law of thermodynamics, provided we're dealing with pure substances which form perfect crystals at absolute zero. I don't care about the mathematics of that part of that statement. I care about it's being viewed from a conceptual, simplest possible conceptual standpoint. So, what we have here is an equality between these things. Or put another way, how does the G state of water solid compare to the G state of water liquid? What's delta G for this, since the equilibrium condition exists? Zero. Which means that the G states of these two samples of material at any point on line AD are equal. Delta G is zero, equilibrium exists. Slope of line AD. Likely you talked about this in 2045. Now the slope as we pictured it in the diagram you see in the notes is exaggerated. The slope is very slight left leaning. I purposely have drawn it so that you can easily see that it's a left leaning slope for line AD. Well, if you pick a point underneath line AD that corresponds to water in the solid phase, and from this point, which would be any point as you look at the diagram between 0 degrees centigrade and minus 22 degrees centigrade. Okay? You pick a point on the diagram at a temperature greater than minus 22 centigrade but less than 0 degrees centigrade, corresponding to solid water, and you move straight up. You're not changing the temperature whatsoever. You're simply increasing pressure. You're squeezing ice like an ice skater does, a hockey player does, when he or she stands on skates and transmits the entire sample of body mass through these thin skate blades. You think that applies a rather substantial pressure? Did you learn the difference between pressure and force in 2045? If you take a balloon and apply a force to it by pressing your thumb at it, okay? You could push that balloon in a whole lot with the balloon remaining intact. Now, try to apply the same force to the balloon using the point of a needle. Can you apply the same force? Why not? Because now the force which you are applying is much more concentrated, isn't it? It's being applied to the surface of the balloon through the head of the needle. Result, pop! And if you do the arithmetic, you'll find out that a much smaller force has caused the balloon skin to rupture, because the pressure was much greater. Right. When I was a little guy, I often laid on the floor in the front room and listened to the radio. We didn't have a TV. 1947, 1948. My father used to regularly walk through the room and stand on me in his stocking feet. Stand on my chest. Here I am. Now, my father was also an avid golfer. What if I'd have held a golf tee vertically to my chest and then he stood on that? Could I be here telling you these stories then? Hell no. I'd be the balloon skin that you tried to apply force to with the needle point difference. So one of the significance of the slope of AD, as we've just discussed, is that by application of pressure, you can cause water solid to become water liquid. And this is one of the reasons why ice skaters can glide across the surface of frozen water, because what they're really gliding across is a very thin film of water liquid. Yet this is still a mysterious thing to scientists, interestingly enough, because scientists thought that if I take water solid and make it so cold that the application of pressure to the surface of the water solid by the mass of the ice skater would still not be sufficient to bring about melting, that now the ice skater wouldn't be able to skate. Too much friction. No water liquid functioning like a lubricating medium. The ice skater still skated nicely. So I don't know what's going on yet. So there's a lot more to it than just melting as a consequence of application of pressure. 21.4, line AB, line which separates solid phase water from vapor phase water. I'm sure you learned that if you go straight from solid form of a material to vapor form of the material, it's called sublimation. If you go in the opposite direction, vapor phase, going straight back to the solid phase without the liquid phase being encountered, it's called deposition. If you call it reverse sublimation, that's fine. You haven't changed anything. I mean, that's fine. To me, reverse sublimation is even more straightforward because I think it will tell you exactly what the heck's going on here. Tell me, what temperature and pressure conditions must exist for sublimation to occur? What kind of low temperature?
You need a low pressure and a relatively...
Wait a minute. Let's talk first about temperature. In order for sublimation to occur, in the specific case of water solid becoming water vapor, look at the diagram. What kind of temperature is required for this change to take place? A temperature which is lower than the freezing point temperature of water. Because if you're above the freezing point temperature of water, you're going to get liquid. You can't avoid it. So, required temperature is T lower than MP solid. Whatever the solid might be. Now, pressure. Now, the way I stated the question to you caused you to be misled. I could tell by some of the responses which were offered. Because you're thinking about a particular pressure. No. We talked about this previously. We're talking now about it again. Let's go back to liquid becoming vapor. In order for a liquid to convert to its vapor phase, we have to pay attention to the property of the liquid which measures its temperature, which measures its tendency to become vapor. What is that property of liquid? Vapor pressure. Same for solid. Students often ask or talk about vapor pressures of gases. Gases don't have vapor pressures. A gas does not have a tendency to evaporate. It's already evaporating. And what property of a gas measures its tendency to condense? Well, if you think about it, you should realize concentration, as well as temperature, but concentration for sure. How do we measure concentration for gases in the atmosphere? What property of that gas would we determine or measure if we wanted to get a handle on concentration of oxygen in this stuff we call air? Partial pressure. The pressure of that gas as if it were the only gas in the system. Anybody know the partial pressure of oxygen in air? Usually observed value? I'm listening. The partial pressure of of oxygen in air. The most commonly reported value, as it would correspond to, for example, the air in this room. I want to know the partial pressure for oxygen in air in this room. Well, let's ask another question. To one significant figure, what do you believe is the total pressure of the air in this room? An atmosphere. Goody. Now, what percent of this gas stuff we call air is oxygen?
20.
What is it?
It's about 28.
Anybody know? Anyone know the percentage of nitrogen in this stuff we call air?
72.
That's 78%. Oxygen 21%. And the remaining gases, whatever they may be, total up to the remaining percentage. So if I tell you that air is 21% oxygen, which is true, and the total pressure of this stuff we call air is 1 atmosphere, what's the partial pressure of oxygen? 0.21 atmospheres. Isn't that 21% of 1 atmosphere? Done. Didn't you do this in 2045? So the other part of the puzzle is, for sublimation to occur, is VP for water solid has got to compare how to partial pressure of water vapor. This bigger than this bigger than this, or equal? What? If it's equilibrium, they're equal. But we're talking about sublimation. Which of these has got to be larger? Tendency to evaporate or tendency to condense? Tendency to evaporate. That's what we're talking about, sublimation. So this has got to exist along with this temperature. A temperature lower than the melting point. Now, related to this happens to be a practical phenomenon, drying clothes outdoors in the wintertime, to which I state, or for which I state, that in certain respects, my grandmother was a marvelous thermodynamicist. Because I was born and raised in Toledo, Ohio. And when I was a little guy, my mom had a lot of health problems, I'm sorry to say. I mean, she ultimately got past those problems. But during those times, I would stay with Grandma and Grandpa. That was convenient because Grandma and Grandpa's house was only a half a block from my grade school. Now, I'm even talking about times before I was old enough to go to grade school. It was little Jimmy. Okay? And Grandma, in the dead of winter, would launder. She would, among other things, bring Grandpa's work dungarees out to the yard. Dryers? 1945? 1946? Didn't have those things yet. So Grandma, in the dead of winter, would bring the clothes out in the yard where little Jimmy was at play and hang up, among other things, Grandpa's dungarees. Now, on clothespinning these water-wet dungarees to the line, given that it was very cold, the first thing happened is that the water-wet dungarees turned into a swinging board as the water liquid became water solid. And then, as if by magic, particularly if it was a windy day, a windy, bright day, sun shining brightly, but the temperature was a good deal lower than 32 Fahrenheit. This Fahrenheit guy must have been a madman. Who the hell would calibrate a temperature system with 32 and 212? This is lunacy. One day maybe this country will wise up and go to the metric system. I doubt it, though. One of the very difficult aspects of life is to realize that in cases that are far too numerous to deal with, stupidity reigns supreme. Well, forget that for now. Let's go back to the dungarees. As if by magic, on this very cold, dry day, the relative humidity was low. These board-swinging dungarees, which would hurt little Jimmy if they hit him, turned into soft, fluffy, blue denims with no water liquid laying underneath on the sidewalk or on the grass. What happened? What happened? Where'd the water solid go? Sublimated. That's what happened. Grandma did this time and again. So I would classify her as a very, very understanding, practical thermodynamicist. Salute to Grandma. More on this stuff in a while. Water liquid at minus 10 degrees centigrade. Can water liquid exist at minus 10 degrees centigrade? Look at the phase diagram. How about minus 22 centigrade? How about minus 23 centigrade? What does the phase diagram tell you about the possibility of water liquid existing at minus 23 centigrade? Does it matter the pressure? Can water liquid exist at minus 23 centigrade? What does the diagram tell you? Yes or no? No. All I'm asking you to do is read the diagram. 21.7. 21.7 we really have already discussed regarding the slope of line AD, but the other point to realize is by the application, if it is true by the application of pressure, we can melt water solid. Which phase, water liquid or water solid? For water solid being referred to as ice 1, the ice with which we are familiar. The ice we make when we put water liquid in the refrigerator freezer at home. Which phase is more dense?
Water.
Water? It's all water. Water solid, water liquid, water vapor.
Water liquid.
Yes, water liquid. So the other important point is to realize, for just about all samples of matter, the solid phase is the most dense. Fortunately, that's not true for common water. Because if it were true, in the wintertime, lakes, streams, oceans would freeze on the surface, as they do, and the surface ice, if it were more dense than water liquid, would sink to the bottom. More freezing, more sink. More freezing, more sink. Pretty soon, in the dead of winter, streams, lakes, rivers, what have you, would freeze from bottom to top. What would happen to marine life? Gone. What would happen to Earth as we know it? Because we would be immersed in an ice age from which practically we couldn't recover. Too much ice to melt. Life wouldn't even be here on Earth as we know it. If it was the case that common ice was more dense than water liquid. But fortunately for us, when we make Kool-Aid and lemonade and iced tea, the ice cubes float. Freezer burn. You all heard about freezer burn? What is it? I want a one-word synonym for freezer burn. If you can give me this one word synonym for freezer burn, then you will be telling me that you got a pretty good idea what freezer burn is. One word synonym. D-E. That's it. Dehydration. That's what freezer burn is. Food, like us, 70-80% water. You take a nice piece of seafood or steak or whatever have you, and you put it in the freezer, unwrapped. How long do you think that food will remain palatable? Unwrapped. Not long, it'll freezer burn. It'll dehydrate. Because in the freezer, we are operating at a temperature which is certainly lower than the melting point of water. And because the refrigerator circulating system continues to take the atmosphere from the freezer, which contains evaporated water vapor, and pull it out. So it keeps creating an atmosphere which is essentially void of water vapor. Well, what's that going to do to this vapor pressure solid compared to partial pressure gas for water? It's going to keep causing the vapor pressure to be larger than the partial pressure, isn't it? Because the gas phase is continuously removed, which means sublimation will continue to occur. And the food freezer burns. So what do we do to stop this? You package the food tightly, and in so doing, inside the packaged food, sealed, so there can be no escape of vapor phase with the contents of the package to the freezer compartment. You establish equilibrium between water solid and water vapor without very much at all of water solid having been converted to water vapor. You got this thing under equilibrium now. So no longer does net transformation of solid to vapor occur in this appropriately packaged food sample. And that's how we stop freezer burn. (21.9). Water solid to water liquid at 25 centigrade. Well, you well know that this takes place at an external pressure 1 atmosphere. You well know if I bring a sample of ice cubes out here and put it in a tray, as we talk, we'll see the ice cubes become liquid. Spontaneous. At 25 centigrade. Can this go this way? Look at the diagram. Now let the diagram talk to you. At 25 centigrade, is it possible to have water solid phase? How about 10 centigrade? Look at the diagram. How about 5 centigrade? Look at the diagram. What's the highest temperature centigrade-wise at which water solid can exist? Look at the diagram. 0.01 degrees centigrade, which corresponds to the temperature at which the triple point can exist. Now, to continue with similar considerations. Water gas becoming water liquid. At 25 centigrade, P external equals 1 atmosphere. What do you think about this transformation? Think it's spontaneous? Do you think it's anti-spontaneous? Do you think instead it might be equilibrium? If it's equilibrium, then partial pressure water vapor equals vapor pressure water liquid. In my periodic table cup, as I do during each class gathering, I have some water liquid. Good stuff. I don't want to spill it, make a mess. So you have to take my word for it that there's water liquid in my cup. Now, at this point, the meniscus level of the water liquid in my cup is down here, coinciding with about the top of the position of the first row of the rare earth metals. Cerium, praseodymium, on down through lutetium. See? 58 through 71. It's about there. If I mark this point, leave the cup stand on the lecture bench, not covered or sealed, will the water liquid level stay there? No. Will that transformation take place? Because if that transformation takes place in this room, given that it's about 25 centigrade in this room, when we come back later and reobserve, the water liquid level will be higher. Will we see that? No. What will we see? That the water liquid level will be lower. Because this system we have, air conditioning system, which does two things. What are the two things the air conditioning system does? It cools the air and dehumidifies, so that we won't get a relative humidity condition in here of 100%, which I believe we mentioned previously. Because if water liquid is in equilibrium with water vapor in this room or any place, then relative humidity of 100% exists. And then we'd sit here, or in my case stand here, and stew about in our own juices. Be very uncomfortable. Because this natural human process of perspiration would not result in any net evaporation of water liquid from our surface. So we would not be cooled by this process. Because evaporation of sweat, liquid to vapor, is an endo transformation. It requires heat. And where does this water liquid that's on the surface of our skin get the heat? From us. It cools us off. So, we need to understand that for the conditions which are with us in this room, this thing is going this way. So this thing is anti-spot. Now then, is it possible at 25 centigrade to make this thing go this way? At 25 centigrade, what would we have to do to make this thing go this way?
Increase the pressure.
We got to make the partial pressure of water vapor compare how to the vapor pressure of water liquid at 25 centigrade. Got to be greater. And then we can have this take place. So, we'll finish with one more question regarding this very transformation. And ask about this interconversion. Left to right or right to left, if we're still at 25 centigrade, but standard state conditions. Is that process at 25 centigrade, at standard state conditions, spontaneous or anti-spontaneous, or equilibrium? See, what I'm doing is to ask you if you understand standard state conditions. That process. Spontaneous. How many vote yes? Do you know that standard state conditions stipulate that the partial pressure of water vapor will be how much?
1 atmosphere.
1 atmosphere. And I guarantee the vapor pressure of water liquid at 25 centigrade is a hell of a lot lower than 1 atmosphere, because the vapor pressure of water liquid does not become 1 atmosphere until you raise the temperature to what value? 100 centigrade. So you betcha that's spontaneous at standard state conditions. We'll pick it up from this point next time.